Let's take some notes about physics. In particular, take some notes about things that are moving at constant velocities. Not a whole lot to say about this. It's a pretty straightforward situation. No pun intended there. It's talking about one-dimensional motion. So things are going straight forward, or I guess they could be going backwards. So first of all, what's the difference between velocity and speed? Why are we using this fancy word? Velocity. Between velocity and speed. Here's the answer. Velocity is a vector, and speed is a scalar. So what is a vector? Vector has magnitude and direction. And speed has magnitude only. No direction. Now, if you're only moving in one dimension, that means basically you're moving back and forth on a line. You can imagine like a number line. That's something that is moving back and forth on. It could be a bigger number line or a smaller number line. It could be a number line like on your piece of paper. It could be a Interstate 81. It's kind of like a number line. I mean, it's not exactly straight, but if you only pay attention to like being on that road, there's mile markers there. It's like a number line. You can move into like higher numbered mile markers. You can move into lower ones from higher ones. And the origin is at the Virginia, Tennessee border, I think. Down there, that's where mile marker 0 is. So there's examples of number lines like that we move back and forth on all the time. And when you're moving only back and forth in one dimension, then when we talk about direction, there's only two possible directions, forward and backward. Well, I shouldn't say forward and backward. I should say like in the positive direction and in the negative direction. So here, that's not really that complicated for us. It just means that in one dimension, velocity can be, that's just can, ignore this smudge, can be positive or negative. Speed is always positive. And if you need a reminder, the thing that's in your car when you're driving around and you look down and see how fast you're going, that is not a velocity meter, it's a speedometer. It measures your speed. And I bet you've never looked down at that thing and seen a negative number. Now, I had some smart aleck student try to convince me one year that some cars, when you were going in reverse, would have negative whatever, but I think that that's not true. So anyway, it's a speedometer. It tells you how fast you're going, but only the magnitude of that. Only how fast, doesn't care about direction. Doesn't care about if you're going north or south or east or west or whatever. So speed is always positive, and we got that nice reminder of the speedometer. All right, so let's define some stuff here. If we call the position x. So if we imagine we're just moving in one dimension, then that one dimension could be like a number line. We could think of it like an x-axis. So position x, can the position of something be positive or negative? Yes. Right? You could be, if we allow for, all the states like to start the numbering over again on the interstates because, it's their state and they want to have their own numbers. You could say, like, if we were going to be Virginia-centric, we could say that 0 is down at the border of Virginia and Tennessee, and then when you cross over that going south, then you go into negative numbers. Now, probably Tennessee wouldn't like that, but number lines have to have negative numbers on them because wherever you pick the origin, unless it's not really a line, unless it's just like a ray that has like a point where it starts and then it goes in one direction, then you could just call the point where it starts 0 and all things go from there. But a lot of situations you can go both directions, so we just have to choose an origin, and then if you go to the left of the origin, then you're in negative territory. So position can be negative. What about this? Delta x, you know about delta stuff. It's the change in. So it'd be like x final minus x initial. And we call that displacement. Intuitively, it's a measurement of how far you are away from where you started. If can it be negative? Sure. If your displacement's negative, it means you're more to the, if we're just saying left is negative and right is positive, then a negative displacement would mean you are more to the left than where you started. All right, and then we have distance, which is the absolute value of displacement. So if you ask me, for example, how far is it, Mr. McGrath, from RCHS to your house? And I said 15 miles. And then you said, but how far is it from your house to RCHS? I would also say 15 miles, even though it's the other way. So when we ask questions about how far, we're really asking for a distance. We're not expecting to get a negative number. So we need to recognize that. All right. So what is velocity? Velocity is, average velocity is defined to be displacement over change in time, right? How far did something go and over how much time did it take? So, this might be in miles, this could be in hours, so you get miles per hour, meters per second, whatever. This is average velocity. Now, of course, if you're talking about things that are going at a constant velocity, then your constant velocity is equal to your average velocity because it's not changing. So for constant velocity, v, I'm going to say Vx for velocity, something that's moving back and forth on an x-axis, is equal to delta x over delta t. The equation of motion comes directly from this. So let's just take this here for a second and play around with it. So let's see, Vx is equal to, what is delta x? Well, delta x is just final minus initial, so x final minus x initial over delta t. And then if I move that over there and just do a little bit of baby algebra, And if we say that instead of like some delta time, instead of some time interval, if this is like the actual time starting from time 0, then, well, let's do it like this. Here, I'll do one more step. So just sticking exactly with these symbols here, it would rearrange into this. But then if we say, okay, let's say time started at 0, so delta time is actually like your stopwatch reading, then that would just become time. And then instead of having my x final, it could be like a running, like real-time location of where we are. So like at time 2 seconds, I'm at this point. Time 3 seconds, I'm at this place, at this location or position. So that's our equation of motion for constant velocity. Your position is equal to Vx times your constant velocity times time plus your initial position. And graph, what would that look like if we graph that? You've already seen it. It's your ping pong ball cannon. So the graph of position versus time would look like this. I'm going to let that extend below because we can have negative positions. So this is my position here, which we are going to call x often because that's the name of our first dimension if we're just letting something move in one dimension. That may be like a tiny bit confusing at the start that we're putting x here on this vertical axis, but it's just short for position. And here is time. I'm not going to put any units on here because I'm not committing to any particular units. Most often we'll do meters here and seconds here because those are the SI units for distances and for times. But it doesn't have to be, so I'm going to leave them blank. And then, well, if you have something moving at a constant velocity, then it's got to start somewhere. So time 0, well, let's say it starts there. It doesn't have to start at the origin. And then if it's moving at a constant velocity, this will be a straight line. And the equation for that line is x equals the constant velocity, which would be the slope of this, times time plus initial position. So when you look at this equation here, you should be, one of the connections you want to make is that this is a y equals mx plus b. Maybe a little bit confusing because there's two x's and I said the letter x when I was pointing to this one, which isn't the only thing that doesn't have any x's in it. But all I'm saying here is that you look at this and you're like, that is the equation for a straight line, y equals mx plus b. This is the thing that's getting plotted on the vertical axis. This is the slope. This is the thing that's getting plotted on the horizontal axis. And this is the intercept, which I should add in here. Right? So x equals Vx times t plus initial position. That is what we are talking about. And gee, I don't think that there's anything else that I need to tell you except for possibly that if you have something that's moving back and forth on a straight line and sort of doing like a constant velocity in one direction and then going constant velocity, maybe a different constant velocity back, then you just have to watch out that total distance traveled means exactly what it means intuitively to us. So if you went from, let's say, Lexington to Charlottesville and back, to Lexington. What is your displacement? And we're just pretending that the whole drive there is just like a straight number line. I know it's not, obviously. You go move completely in 3 dimensions, north, south, east, west, and up and down. But we're just going to pretend that it's one big number line to get there. So what would your displacement be when you go from Lexington to Charlottesville and then back again? It would be 0. What would your total distance be? Well, total distance just adds up all the positive legs of your journey. And just like back to the car again, your odometer, which is the little thing that keeps track of how many miles your car has ever driven, your odometer keeps track, and it keeps ticking upward always, regardless of what direction you're going. That's like a total distance meter. So your car is keeping track of your speed and your total distance, not really caring about what direction you're going in. So what would the total distance traveled? Well, Lex to Seaville's, I don't know, maybe let's say 70 miles or something, and then back to Lex again. So that'd be approximately 140 miles. So it's the same trip. But if we talk about the displacement, since you started and ended in the same position, that's 0. Total distance is about 140 miles. Why do we have 2 different things? I think that should be clear. If you're interested, it just depends on what you're interested in. Often it's nice to know both. But for displacement here, if you borrowed your mom's car and she's like, "Where's the car?" and you did this trip here, you'd be like, "It's in the driveway, Mom. Same place it was this morning." So that's, displacement is important there. And then if you borrowed some money from your dad to pay for gas, then you're like, "Look, the car's right where it started." And Dad's like, "Yeah, but you put 140 miles on the car. You need to spend some money on gas for that, right?" So they're both important things. Let's see. I think that that is all I'm going to give you for your constant velocity notes. So I'm going to try some problems in the book, and I'll make some videos to go with those, and it will all be fun and great.